Okay, so I'm going to go through this installation of capacitors and transformers in this section here. I'm just going to kind of hit through the module for the most part. They kind of just show you the general sections here right off the bat for installation of a liquid filled electrical equipment. So that could be a transformer or a capacitor. They both have dielectric liquid. And a transformer it's used for cooling, and a capacitor it's used for insulating. But the biggest thing I'd say to watch out for is like subrule 1 tells us that specific amounts of liquid in either a capacitor in a tank or in a group of tanks, so that's again a capacitor or a transformer, has to be installed in an equipment vault. So that says that right straight in there. But if you keep reading, it says unless it meets the requirements of subrule 5. So a lot of these rules will state something word for word and say this must be done, but then it also lists the exception right after. Okay, and we'll see that in transformer calculations when we come up with them too. But just keep reading is what I would say. That's the biggest thing. Subrule 3 again allows for motor starters to have the 2 times the liquid of the equipment. So you can basically double the amounts of all of the previous liters if it's a motor starter. So just make sure you're reading through each one of these rules carefully, and it'll go through and tell you exactly what's needed and then the exceptions. But again, just make sure to keep reading through. Okay, so then it's going to go through outdoor installations, substations. It's not too terrible. The one thing I would definitely show though is this question here, question 5. So a service room is to have the following equipment mounted side by side on the same wall, so not in a corner. That's from Appendix B. So mine, it's page 665, but I'll show you what they use to get those values. So this is where it's talking whether we're in the corner, or sorry, open floor, against a wall, or in the corner. And then we're going to get how far away from these pieces of equipment does anything else have to be. So in that question, it said we have a 30-liter tank. And again, it's against the wall. So that's this column right here in the middle. So if we get a 30-liter tank, it needs to have 1.25 meters buffer, if you will, from anything else that's near it. So if we have that capacitor on the wall, and then also it said 15 liters for each of 3 transformers. So that's like a bank of transformers. So we would take that 15 times it by 3, get to 45, and we'd go and see that it's 1.53 from the transformers. So we kind of just take both of those, add them up together, and you'll get the 2.78 that it's looking for here. Okay, so you have to use Appendix B for those calculations when it's talking about against the wall or in the corner or anything like that. The next thing it goes through is power factor correction, something obviously we've done already. You can do it the way the module does it, or just do it the RLC way. Okay, it's either way, it's going to work out fine. I do it the RLC way because I'm comfortable doing it that way, and it works just fine. When we do power factor correction, the one thing we've got to watch out for is if the power factor correction, if the capacitor bank is on the load side of the motor starter, we're still correcting this guy's power factor, but we're doing it before the overloads. That's the big thing. So these overloads are normally sized off the FLA for this motor. If we do power factor correction, we have to use the corrected current to size these, because that's what they're going to see. They're going to see corrected current, not motor current. Okay, so make sure if you have the bank in this location, that we are sizing these overloads for the corrected current. You still use the percentages from your service factor with the new current, but we make sure we use that corrected current for these calculations. Okay, so then it goes through and tells us how to do power factor correction. Again, I can post some questions here coming up. I'm trying to use this Blackboard collab to record my videos because I'm having issues with Camtasia. So Then it talks about power factor for a group of motors. Again, we did something very similar to this earlier on in the course. Just take all the lagging loads, add them up, and then only bring your watts over to your triangle when you want a new power factor. If you're correcting it to 0.9, only bring the watts over, find the new VARs, and then you'll be able to see what value of capacitor bank you need to get to those VARs. It's, again, very similar to what we did already. But if you have issues with any of them, just let me know, and I can do some examples for you one-on-one as well too. But I'll pick a few and maybe post some examples here coming up if I can get this to work. So then again, here's where it's really talking about what objective 3 is talking about on the load side of the motor. So that's when we have it here. Again, this is on page 20, where it's actually saying these overloads must be determined according to the power factor corrected current. Okay. So, and it says we don't need a disconnect because the motor controller is going to disconnect this bank, and we don't need discharge resistors because that's saying in the code that we do have to have them, but we don't in this case because they're going to discharge through the motor windings. Okay. Just kind of going through. Okay, so conductor sizing for capacitor circuits. So we did this in second year as well. Basically, when we're deciding the size of the branch circuit, we just take the current of the capacitor bank and times it by 135%, and then we go to table 2, and whatever the temperature termination is what we're going to use to find the wire. Okay, so this one actually gave us the VARs instead. So just make sure you know whether it's a 3-phase or single phase before you get down to current. This one's a single phase in this example. So you just divide by 240, get your current times by 135%, and then you get your current that you're going to use to go size your conductors from. Now, again, watts determination temperature on these, and I'll show you an example here where it kind of can get a little greasy on us because there's more than one temperature termination. So in this example, they actually say we have 2 capacitors, so we're going to have tap conductors. So we can have tap conductors, and they're going to say that the breaker feeding the branch is going to be enough to cover the taps as long as it's 1/3 of that branch circuit wire ampacity. So we always want to double check that too, but ultimately we're going to do it the same way, where we're going to find the current of the capacitor. We'll get the tap conductor minimum ampacity by using that current that each capacitor is drawing. So each capacitor is drawing 18.1 amps, times that by 135%, and we'll get 24.4 amps. So that's for the taps that we're going to size. The branch circuit, we're going to basically just say, hey, we have 2 capacitors. So we're going to add them together or double it, and we'll get the increased current for the branch circuit. So we size the taps off of the 24.4 amps in this case, and then we size the branch off the 48.8 amps. Now, the thing that's important here to look at, if I can show it a little bit closer here, is this scenario here that we have going on. So it said we have a 75-degree circuit breaker, then we have splice or tap connections that are rated at 110, and then we have capacitors that are rated at 90. So if we're sizing the branch, that's this circuit from here to here. So our termination temperatures are 75 and 100. So that's why we're using 75 to size the branch. Then when we look at the capacitor for the taps here, we're looking at 100 or 90. So we always go with the lowest. So that's why we're choosing 90 for the tap conductors. Okay, so watch your termination temperatures on these questions too, because they'll kind of mix it around on you. This is a good kind of recap of everything. This scenario they got going on here kind of tells you everything you need to do. Oh, the breaker size too, we just go to 250%. That's a maximum though, so we go down from that. Okay, watch that too. If in the code rule it ever says it can be lower, or if that's a maximum, that percentage, then when we size our breaker from table 13, we always have to go down. Okay, so we got to make sure we're just reading that carefully. If it says that that's a maximum, we have to treat it as such. Okay, so when we go to the overcurrent protection for a capacitor 26210, it says an overcurrent device rated or set as low as practicable without causing unnecessary opening of the circuit, but not exceeding 250%. So we're going to use that 250%, but we can't exceed that. So if we get a value from that, we have to go down when we go to table 13. Okay, so that was right out of the code there. I'm going to go through capacitors disconnecting. Just watch too. Again, they go through the examples. They hit you on all these things, which is pretty, again, I think the code does a pretty good job in this module. Is the contactors too. Make sure if you're an enclosed or if you're an open contactor, you'll get a different percentage when you're sizing your contactors. And then for the disconnect switches, again, it's straight out of the code, telling you to just basically use 135% for your rating of your disconnect. So definitely go through these Objective 4 exercises. It's going to get you through every type of capacitor sizing question that you're going to see. Okay, so if you can get through these guys, you're going to be doing okay. Here's one of the questions here where they give us multiple termination temperature ratings. So just make sure, and what I do is just draw it out. Then I can see the branch has 90 and 110, and the taps are 75 and 110, and that's going to tell you whether to choose 75 or 90. And you can always check that we're a third too, okay, just like they did in the example. So I still check to see, is my minimum wire here for the tap, this 35 amps, is it covering at least a third of this one? And yes, it is. So we're good to use those. Okay, so definitely go through those as well too. Okay, so then we're going to talk about transformers. Again, the biggest thing here is making sure we read the rules, okay? Because you're going to get some where you're going to think, oh, I just read that word for word. But if we just keep reading, we're going to see that there's a difference, okay? So they first start talking about sizing conductors. So they talk about sizing conductors for a single transformer here, again at 125% of the rated primary current. And then they talk about parallel connections as well too. So if we have more than one transformer, what we have to do. And again, the rules are pretty, I think, again, straightforward, okay? But in this example here, saying that, again, watch it if it's single phase or three phase, because they're always going to give us a VA usually, and we got to find the current. So if they give us a VA and we're using the S total formula to find our amperage, we have to make sure we're using the right voltage and potentially √3 if it's three phase. So, and the other thing to remember is VA in equals VA out. So if the VA on the primary is 37.5 kVA, the VA on the secondary is the same. Okay, so what they do is, let's say we want to find out the wires that are feeding this transformer. So we have our, to find our I line for our primary, we take our VA, we divide it by 600 volts, and get our amperage. Then the rule tells us to go 125% of that. So rule 26256 is saying, number one, the conductor supplying the transformer shall have an ampacity rating not less, so this is A, subrule A, not less than 125% of the rated primary current of the transformer for a single transformer. So that's what we're dealing with. We don't have ones in parallel here. So this is how I do these questions. I try to draw them out every time too. It seems to help me get through these and make sure I do it right. So this is kind of what I do, is I draw the transformer. So there's my primary, there's my secondary, and in this, here's my load. So they want to know what this conductor is here. So I'm going to take my VA, divided by my voltage, get my current. So this is the same example. This is how I lay it out. Times it by 125%. I get my current of my wire, and then I go to table 2 under the 75 degree because that's what it stated. It says the transformer is rated at 75 on the primary and secondary, and all other equipment is 90. So if it's got that 75 rating on the primary and secondary, that's where we're going to go for our wire. So do the same for the secondary now. Take that VA divided by the secondary voltage now, and we get a different current value. Obviously on the secondary, much higher because our voltage is quite a bit lower. So now we have 156.3 amps. And we times that by 1.25, and we get 195.4 amps. And that's what we're going to go to size from table 2, and we get a 3/0. So I'd need to have a number 4 right here on my primary, be number 4, and here I'd have 3/0. Okay, so that's how we're going to size these conductors. Now they go through another example here on the next page about parallel. So again, the rules are somewhat straightforward. If you read, it says for the conductor size, it's part B of sub rule 1, where it says the conductor supplying transformer shall have an ampacity rating B not less than the sum of the rated primary currents of all the transformers plus 25% of the rated primary current of the largest transformer for a group of transformers operated in parallel or on a common feeder. So on the primary side, we're going to take the largest value of the largest transformer, times that by 125%, and then we're just going to add the rated primary currents of the other ones. Okay, that's how we're going to do the primary. So if we look at this question, it's saying we got 2 transformers. It's going to get the rated current on the primary for both. So we have 2 single phase. Again, they're single phase. Lighting transformers are operated in parallel from a 2400 volt supply. One is 25 kVA and the other is 32.5 kVA. The secondary voltage is 120/240 and all the equipment's rated for 90 degrees. So they want to know what the minimum size of the primary and secondary conductors are. So the primary conductor, again, we use the ES total formula. We're going to find our current here for the 32.5 kVA, and we're going to find the current here for the 25 kVA. So what they're saying is we take the largest one times about 125%. So that's what they're doing here. The largest one times 125% plus the primary current of the other transformer. Okay, or you can do like they say exactly in the rule, is they're going to take this value plus 25% of this value, which is the same as using 125%. Okay, so I do this way, but do whatever way works best for you. You get the same answer. Okay, and then it says we go to table 2 and we can pick number 12. The calculated current of the largest transformer, again, now we're talking about our secondary. So we're going to use the same VA, but we're using the secondary voltage now, and we get our secondary current. And then we do the same for this transformer. We take the VA and the secondary voltage, they were both 240, and we're going to find the current there. Now this rule for the secondary is basically telling us that we want to make sure, it says, so the secondary conductors connected to the transformer shall have an ampacity rating. If we look at the parallel, says not less than 125% of the sum of the rated secondary currents of all the transformers operated in parallel. Okay, so we basically need to take 125% of all of the current, so both of them. So the 135.4 and the 104.2. So we add those together, get 239.6. Then we times that because all of them get times by 125%. And there's a mistake in this module too. They're saying it's rule 258. It's actually 256. Okay, just so you know. So again, what I do is usually I try and draw this out. It's the easiest thing for me. So I have my primary conductors coming in here. So I found my primary current for this guy here, primary current for that there. Now the secondaries, again, there's my secondary current and my secondary current. Again, I just draw this out regardless, just so I can see exactly what's going on. I know that it's the same VA on both sides, primary and secondary, and I can get these two currents. Then I can do my calculations based on the fact they're parallel. So again, on the primary, we take the largest times 125%, add the other one, and on the secondary, we take all of them times 125%. Again, that's just because we are in a parallel scenario. Okay. So now we have a 3-phase one on this example, and it's talking about we have a 50 kVA 3-phase transformer. Okay, sorry. Fed from a 480 volt system. All equipment on the primary is rated at 90 degrees. The secondary of this transformer is rated at 90 degrees, 120/208. and provides power for wall outlets and lighting in an office building through a panel with a main breaker rated at 75 degrees. It is a very common scenario that we would do in a lot of places that have shops and offices or work areas that need 120 volt plugs, because we may have a 600 volt service coming in. So we get our primary to size our conductor. We get our primary current. Again, watching this time, because it's 3-phase, we got to make sure and use root 3. Okay. Then we would watch our termination temperature. Again, it says all equipment on the primary is 90 degrees. So if we size the primary conductors, we're using the 90 degree. The secondary is rated at 90, but the panel of the main breaker is rated at 75. So again, I draw this out to help me out here, and I hit my VA on my primary and my VA on my secondary. Again, same. Take the voltage of my primary, again, using root 3 because it's 3-phase, and get my primary current. Then I can get my secondary current, but using the 208 of my secondary voltage. Then I go back to the rule for sizing conductors. I take 125%. I get my new calculated value, and I go to the 90 degree because it said all terminations were 90. So 90 here, 90 here. On the secondary, it says there's 90 degree on the secondary, and I'm going to a 75 degree breaker in the panel. So I'm going to use 75 degree when I size this one. So I take my secondary current, still times by 125%, and then I'm going to go and take that value to table 2. Okay, so just watch out for that 3-phase thing. Otherwise, that question is exactly the same as the other ones we've done. Now, overcurrent protection. This is where things get a little bit greasy, if you will. Sorry for using that term tons, but there's a lot of greasy stuff going down here. We want to make sure, really make sure and continue to read here, okay? Because there's some stuff to watch out for. So there's some terms here we got to watch out for as well too. So when determining the size of the overcurrent protection for a transformer rated over 750, we refer to Rule 26.250. So Rule 26.250 literally says overcurrent protection for power and distribution transformer circuit rated over 750. Okay, so that's where we're going if our voltage is higher than 750 volts. Okay, and then it says the first rule literally says loaded with exceptions. So except as permitted in subrules 2, 3, and 4, each ungrounded conductor of the transformer feeder branch circuit supplying the transformer shall be provided with overcurrent protection. A, rated at not more than 150% of the rated primary current in the case of a fuse. Okay, so if we have a fuse, it's going to be 150%. Or B, rated at set at not more than 300% of the rated primary current in the case of breakers. Okay, so basically that's telling me if I get a fuse, I'm going to, my maximum, so rated at not more than 150% is going to be for a fuse. And same thing with the breaker, not more than 300% if it's a breaker. Okay, so that tells me in my head, those are maximums, I'm always going to go down. But if we read Rule 2, it says where 150% of the rated primary current of the transformer does not correspond to a standard rating of a fuse, the next higher shall be permitted. So if we're doing a fuse, it's not at 150% isn't the maximum. If we get between two fuses, we're actually going to go up. But it only says that for a fuse. It doesn't say that for a breaker. So for a fuse, we're going to go up, but for a breaker, we're going to go down. Okay, which again can be confusing, but it says that specifically right in the rules. So again, these ones, keep reading, read all of the exceptions before you decide what you're going to do. So if we look at this scenario in the module here, it's single phase. We've got our primary disconnect. So again, here's our transformer, our kVA listed, and it's got our output too. So it's saying if we take our primary current for the transformer, we get our value, again, single phase, so we don't have to use root 3 here. We get our value of 17.7 amps, and because it's a fuse, we're going to take that times 150%. Now normally, again, we would think that we would have, that's a maximum, but sub rule 2, so it says right here, even in your mod, sub rule 2 states that if the overcurrent device is a fuse, the next higher standard rating may be used. Using table 13, a list of standard available devices to select from, The maximum standard rating of the primary overcurrent device of the transformer is a 30 amp fuse. Okay. Subrule 1 also states that if it's a circuit breaker, again, this is telling you if it's a breaker. Subrule 2 doesn't mention about going up to the next one if it's a breaker. It only says for a fuse. So if we're using a breaker, we go to 300% and we go down, okay, because that is a maximum. So watch out for that. Okay, if it was a breaker, they just go through the scenario here. We would times that by 3, we get 53.1, and then we go down to a 50 again, because in a breaker we have to go down. Okay, so in the second example, again, they go through these examples really well in this module, I find. Okay, and it's basically read the rule while you're going through it. There's something to make a distinction here too between the primary feeder circuit breaker and the primary disconnect. So in this previous example, we had our primary disconnect, and it was basically this fuse right here above the right above feeding the transformer. In the next one, we talk about this next example. We're seeing that it's labeled different. It says primary feeder circuit breaker. Okay, so that's different. That's basically our disconnect would be right here, but this is a primary feeder. Okay, so there's a distinction between that, because what they're saying is we can eliminate that primary disconnect that we saw from the other example if we have a disconnect on the secondary side. So we still have our primary feeder, but we may be able to get rid of the fuse that should be right there, okay, if we have one on the secondary. So it says an individual overcurrent device on the primary side of the transformer is not required if there is overcurrent protection on the secondary side, and if the feeder branch circuit overcurrent device provides protection specified in Rule 26.254. So 26.254, Subrule 4, sorry, says a transformer having an overcurrent device on the secondary side rated is set at not more than the values in Table 50, or a transformer equipped with coordinated thermal overload protection by the manufacturer shall not be required to have individual overcurrent device on the primary side, provided that the primary feeder overcurrent device is rated, it said, at not more than the values in Table 50. So Table 50 is talking about this guy right here. Okay, so it says the transformer has an overcurrent device on the secondary side. So this overcurrent device is set at the values in Table 50 using the rated secondary current and the impedance of the transformer. Choose the nearest standard rating at or below the calculated value. So there's also a primary feeder overcurrent device. So that's what I'm reading here. The device overcurrent is set at the values in Table 50 using the rated primary current and the impedance of the transformer. Choose the nearest standard rating at or below the calculated value. So in this example here, we have our primary voltage coming in. We have our kVA. They've given us our percent impedance because that's important to us now, and our secondary voltage. So it says calculate the maximum standard rating of the feeder circuit breaker on the primary side. So again, that's the primary feeder circuit breaker on the primary side. So we calculate our primary current using our VA and our voltage in √3 because it's 3-phase. And then using Rule 26.250 and Table 50, the maximum rating of the feeder circuit breaker is, so let's go to Table 50 and have a look and see how they're getting these values. Okay, so if we look at Table 50, this guy right here, so we want to look at our percent impedance, so not more than 7.5 or more than 7.5. We're at 4.6, so we'll be in this top section here. And then we have to say the maximum rating or setting overcurrent device as a percentage of rated current. So we're going to see that is it over 750, which it is because we're at 2400 volts. Is it a circuit breaker or a fuse? And this one is a circuit breaker. So that's where they're getting the 600% from, okay? And if we were doing it on the secondary side, that's this section here, okay? And it's all based on the voltages, okay? So that's where they got this 600% from. So we take that primary current by 600%. So based on table 13, the maximum standard rating of the feeder circuit breaker on the primary side of the transformer would be 175 amps. Now calculate the standard rating of the circuit breaker on the secondary side of this transformer. So we get our secondary current, 125.1. Then using rule 26-250 and table 50, the maximum rating of the secondary circuit breaker. Okay, so we go back to table 50 and we can see that, again, we're still in the same section with the percent impedance. Sorry, I'm doing my best here. Make sure you guys can see this well. And we're gonna zoom out here. Okay, so now we're gonna see that, again, we're still in the not more, but now on the secondary side, we're at 600. So we'll be at 750 or less, and it's a circuit breaker. So that's where we're getting the 250% from. Okay, so then we say based on table 13, the maximum standard rating of the circuit breaker on the secondary side of the transformer is 300 amps, because that's a maximum, so we're going to go down. Okay, transformers rated at 750 or less other than dry type, so that would obviously be wet. So that's a separate rule, 26-252. So these are the first things we're going to do, is we're going to say what type of transformer is it when we're deciding the overcurrent. What type of transformer is it? What's the voltage rating of it? Because that's going to get us into a different overcurrent scenario. So this rule 26-252 says overcurrent protection against 750 or less other than dry type. Okay, so and it says that right in the bold heading of the rule. Okay, so now we're into this guy right here, other than dry. And again, the first rule literally lists exceptions. So except as permitted in subrules 2 to 6. So all of these are exceptions. So read carefully through all of those. Okay, but let's look at this example here. So we have example 3 here. We got a drawing here. We got a dielectric liquid filled transformer, because it's on dry, and less than 750. So subrule 1 states this type of transformer is to be protected by its own overcurrent device on the primary side. The rating of the overcurrent device is calculated at not more than 150% of the primary current. So like most of our examples here, we're going to have to find our primary current. So it's a single phase transformer. Going to take our VA divided by our voltage, and we get our primary current, and we're going to use 150%. And it says select the maximum standard rating overcurrent device on the primary side. Subrule 2, again, some of the exceptions, states that because the rated primary current is greater than 9, and if the calculated overcurrent rating does not correspond with the standard rating, the next higher standard rated overcurrent may be used. So we can go up. Okay, so in this case, we go to table 13, and the standard rating of a primary overcurrent device, again, this is a circuit breaker, is 20 amps. So again, it didn't make a distinction between is it a fuse or a circuit breaker. It just literally says where the rated primary current of the transformer is 9 amps or more, and 150% of this current does not correspond to a standard rating of fuse or non-adjustable circuit breaker, the next higher shall be permitted. Okay, so again, that's telling us even though they say that 150 is a max, we're allowed to go up. Okay, so it's kind of not really a max, but read the exceptions. Okay, or you're going to get caught up in doing something, finding the rule, obviously doing it, which what the rule is saying, but you got to read the exceptions. Figure 19 represents dielectric liquid filled transformer rated 750, less than, sorry, 750. So, and we can see that here, obviously it's 600 volts, single phase. The overcurrent protection, again, we're going to take our VA, so the 1 kVA divided by our voltage, get our current. This point, our current is going to be quite a bit smaller. So calculate demand required for the overcurrent on the primary side. Subrule 2B states that because the rated primary current is less than 2 amps, the rating of the overcurrent device is calculated not more than 300% of the rated primary current of the transformer. So again, that's because we are less than 2 amps, and it says that rate in the rule. Okay, so Rule B says less than 9, an overcurrent device rated at set at not more than 167% of the rated primary current shall be permitted, except that where the rated primary current is less than 2 amps, an overcurrent device rated set at not more than 300% of the rated primary current shall be permitted. Again, it says not more than 300%. Okay, so we would say we're going to go use that, calculate the standard rating. Subrule 2B also says to choose a standard overcurrent device based on your calculated overcurrent rating, which does not exceed or is lower than your calculated rating. Okay, so that's a maximum. Let's see, 26252, in this case, transformer. On the secondary side, okay, so it's talking about subrule 4 now. So example 5. So again, these examples are going through all these little subrules as well too. So in this case, the liquid-filled transformer has an overcurrent device on the secondary side. Subrule 4 states this overcurrent device is rated at set at 125% or less based on the rated secondary current. There's also a primary feeder overcurrent device. This overcurrent device is rated at set at 300% or less based on the rated primary current of the transformer. If both of these conditions are met, this transformer does not need an individual overcurrent on the primary. Okay, so we don't have to have this if those conditions are met between the primary feeder circuit breaker and the secondary. So we're going to calculate the maximum standard rating of the primary feeder overcurrent device, and we're going to get our VA divided by our voltage, get our current. Subrule 4 states the maximum rating of the primary feeder overcurrent device is 300%. So we take that current times 3 and we get our value using table 13. Again, that's a maximum, so we go down to a 110. The maximum standard rating of the secondary, again, we get our secondary current. So 98.3. Subrule 4 states the maximum rating of the secondary overcurrent device is 125%. So we find our new value of current with 125%. Now, 26252.5a, because the rated secondary current is 9 amps or larger, you are allowed to choose the next higher standard rating overcurrent device on the secondary side. So we can go up for that, again, because that's what it says in the rule. Okay, and then it talks about dry type next, 750 or less. Subrule 1 states that except for certain conditions as set out in Subrule 2, a dry type transformer is to be protected by its own individual overcurrent device on the primary side. The rating of the overcurrent device is calculated at not more than 125% of the rated primary current of the transformer. If the calculated overcurrent rating is not a standard rating, Subrule 3 states you can select up to the nearest standard rating. This overcurrent device is also considered to protect the secondary conductors, which have been rated for 125%, at least 125% of the rated secondary current. Okay, so this is dry type, so it gets us into rule 26254. Again, 750 or less. So in this, it says to look at figure 21, so this is example 6 here. So this is the figure 21. It's going to be down here, and this guy right here. So they draw them out too. Again, I would suggest doing the same. So we calculate the maximum standard rating of the overcurrent device. In this case, it's a fuse. So we get our rated primary current, 75 kVA divided by 600. Again, it's single phase. We get our rated primary current, and then we times that by 125%, and we get this new value of current. So then using table 13, the maximum standard rating overcurrent for this would be a 175, because subrule 3 is allowing us to go up. Calculate the size of the R90 secondary conductors. Okay, so we get our secondary voltage now instead, get our current times by 125%, and we're going to use 195.3 amps, and that's how we're going to size the conductors. Okay, so we would say that we have got our fuse here based on the first part of that rule, and then we went back to rule 26256, which is sizing the conductors if they want to know what the size of the secondary conductors are, which is 125%, just like the primary. Okay, again, watch your termination temperatures. And then they kind of give you a little shortcut here. I don't want to say it's a shortcut. It's kind of a flow chart of all of the rules. Okay, I would say just read the rules. But if you want to use this to help, is it over 750? No. Is it dry or wet? If it's dry, go this way. Okay, so use it for what it is. It's going to show you basically all the stuff that all this exceptions, all that kind of stuff. Again, I would just read through the rule myself, but do whatever's easiest for you. So that's kind of long and short. Again, sorry about I was having an issue with my Camtasia, so I did use this. Hopefully this works out good. Definitely go through this mod. It's not too terrible to go through, work through the objective exercises, and then go through the blackboard, and you'll be set.